Welcome to Track E. This is the international track. I'm Carl Gerber, Chief Data Officer for Deloitte US. The MIT CDOIQ Symposium continues to expand our global reach. We have an excellent lineup of sessions that bring a world view. This is session 10E, Automated and Autonomous Vessels and Dilemmas of Data Sharing in Maritime. This presentation will focus on challenges of data sharing in maritime, and we'll also look at the solutions that have been piloted in the autonomy domain and what kind of data sharing is needed in order to succeed in the field of autonomy. This presentation will also provide latest update to current state in maritime autonomy and what lays ahead. A few housekeeping points about our session. It is being recorded, and this, and as well as all the other sessions together with the presentations, will be made available to participants following the symposium. We do have a Q&A session, and so you have the ability to put questions in the Q&A tab in the Wahoo app. And if you see a question that you like, please vote it up, and we'll be sure that it gets addressed. Now I'd like to introduce Iiro Lindborg, co-founder and VP of Customer Solutions and Concepts at Groki Technologies. Iiro is one of the founding members of Groki Technologies, which is a technology company working on autonomous vessel technologies and solutions. At Groki, he is also Vice President for Customer Solutions and Concepts. In the beginning of his career, he joined Rolls-Royce, now part of Kongsberg Maritime, in 2005, and held various roles such as Development Project Manager and Technology Project Manager before his role as Vice President of Remote and Autonomous Operations. He has a degree in Automation and Electrical Engineering from Vasa University of Applied Sciences. Iiro, over to you.
Thank you very much. So my background is that I've been working in maritime industry for all my career. And in this presentation, as mentioned, I will be focusing on autonomous vessels and data sharing of autonomous vessels also, and also in maritime in general. I'll start off with a bit of a background to maritime itself. One of the challenges in maritime at the moment is that everyone wants to share the data. And that's the hot topic in maritime overall. So data is something that should be shared and used everywhere, but the challenge is that no one wants to share their own data. This also means that the ownership and protection of the data is the biggest issues in the industry at the moment. And that's also the biggest bottleneck at the moment. So it's stopping things developing quite a lot as well. There are many reasons why different companies do not want to share their own data, but the main thing is that they're really protective and thinking that if they would share the data with others, then the others would start to know what their business secrets are and how they're doing business. But hopefully this will change over time. But at the moment, it's, as mentioned, it's the biggest bottleneck in the industry itself. Just a few words about the background of commercial maritime. So I will be focusing on commercial maritime, not talking about naval applications or naval maritime at all. Commercial maritime is really old-fashioned industry and also a self-protected industry. In general, if a new technology comes into general industry and it started to be used, then it will take around 5 to 10 years before that technology is introduced in the maritime domain. In recent years, some of the applications or some of the technologies are coming a bit faster. For example, AI is something that we have seen introduced especially in the optimization field in recent years. But overall, the underlying technologies are being introduced really slowly. Just as an example, touchscreens are still rather new inventions in vessels. So that gives you some kind of perspective how the industry works. Also, cybersecurity is something that where the awareness is increasing all the time, but maritime is way behind of other industries in this domain. And some of you may be aware of the incident some years back with Maersk, where they had a cybersecurity breach, which caused them a lot of troubles. And actually, they went back to pen and paper in many ports around the world in order to get the goods moving when all of their systems were down. The general thinking regarding cybersecurity in maritime is that our systems are isolated because they are on a ship, they're sailing, and they're not connected in any kind of web applications, but that's not true. So there are vulnerabilities in the systems, and they are still people are able to penetrate the systems if they want, although that may be a bit more difficult because of the connectivity issues and things like these, but it's still possible and a real threat as well. The industry itself is really scattered. The total global fleet of commercial maritime is around 120,000 ships. But if you, for example, take the top 3 container ship owners globally, then you can see from the slide that the biggest one, Maersk, has 556 ships out of the total bit more than 5,000 vessels. So it's really scattered, and most of the owners globally have only a couple of vessels, so they may have one to 5. I would say it might be the average in that sense. The other top 3 companies are MSC and CMA GGM, and all of them have between close to 400 and a bit over 400 vessels. But ships are really important part of the global trade. So they carry 90% of the world's trade. And you can see from the top right-hand corner, you can see an illustration or a heat map showing the traffic density globally. So you can see where ships are going, or the majority of them are going. And as you can see, the northern route is not in use at the moment. There has been a lot of discussions because there has been some possibilities to utilize that as well. So if the northern passage would be used, it would be the shortest way from Asia to Europe instead of going through the Suez Canal, for example. And we all know what happens if there's an interruption in the Suez Canal, how big impact that will have globally as well. So there may be needs for alternative routes in the future as well. And it's a similar case also with the Panama Canal as well. So if there would be some kind of blockage or failure, then that would have a significant impact also on the global trade. Then if we look at the ships in general at the moment, so overall 40% of the ships globally are older than 25 years old. And from the illustrations on the right-hand side, you can see a ship built in 2000 and a ship built last year. And as you can see, there's not that much change. So basically the ships are still more or less the same than they were 20 years ago or even 30 years ago. So in that sense, if you look at the vessels, how they look, then not that much change. I think the main change is what we've seen is then on the technology side. So the systems are more up to date, but still a lot of these new vessels also rely on very old technology. Some even are relying quite heavily on systems that have been developed in the 80s and they are still in use today. So the average age of world's commercial ships at the moment is 21 years. And to put things in perspective, the onboard technology when these vessels were new, then Nokia 331 was the coolest and the newest mobile phone, for example. Broadbands were being introduced to homes and businesses. They were nowhere near being introduced on vessels back then. Facebook, Twitter, and YouTube was not even invented yet when these vessels came into operation. So that's the technology on board these vessels today. And you can imagine that these vessels are not that kind of data hubs that would be sending you all the data all the time as you have, for example, with the with cars and trucks today, where they are more or less moving data hubs. So this is not with ships, because the technology is really old. A lot of the connections are still analog, not fully digitalized yet, and so on. So those are the challenges on the kind of infrastructure side at the moment. And also connectivity on these vessels is one really big challenge, because there is no global connectivity available. One can of course use satellite connectivity to get data from vessels, but that's really expensive, because how satellite communications work is that you have to reserve the maximum bandwidth you intend to use, if you use it or not, and you pay based on that maximum bandwidth that you reserved. So you may end up paying 100,000 euros a month for the satellite connectivity, and you may not even use it at all during your voyages. So that's one big issue for the industry. Then one of the hot topics at the moment, I think, is a global hot topic, not just for the maritime, but it's the environment issues. And here is just a current chart of in the EU who are the top 10 polluters. And the first time in this list, there is one shipping company, MSC, who was on the top 3 companies, number 2 in the container ships. So it is becoming a real big issue also, the pollution generated by the vessels globally as well. All the other ones are more or less coal power plants and such. To address this environmental issue, there is a target that ships built between 2020 and 2024 will have to improve the energy efficiency by 15 to 20%, depending on the ship type. And there are different kind of actions taken in order to achieve these efficiency targets. One is to use alternative fuels. LNG is coming, so liquid natural gas is coming as one of the main sources of fuel to compete with heavy fuel oil. Then use alternative power sources like batteries in addition to diesel engines, and other such solutions are being also developed. Then the use of scrubbers has increased in vessels. So scrubbers are washing away the pollution out of the emissions. Then we have the digitalization, so through optimization and different kind of digital approaches. And then the last one is electrification. So a lot of, for example, hydraulic systems are being converted into electric systems and more energy efficient solutions as well. And just one example on the effect of, for example, digitalization in the emissions is that by reducing the ship speed by 10%, this will lead to a 27% reduction of the ship's emissions overall. And this is also a reason why something called just-in-time concept has been developed in many different aspects recently, and I will introduce this concept in more detail later on in this presentation as well. Then going into data exchange within shipping, here's one example of transporting avocados. So a container of avocados going from Mombasa, Africa, into Rotterdam in Europe. The transportation of one such shipment can involve over 30 parties, close to 100 people, and there are 200 information exchanges on this relatively short route involved in the whole process. And there was a study that looked into these information exchanges and what was kind of how they were done. Some of them were electronic, some were on paper, some were on handwritten delivery notes, and some were almost like post-it notes. And this is one of the main issues in the maritime overall. So the data is really scattered around in different sources, and still in these modern times, a lot of the data is being transferred in handwritten notes and post-it note type of information. So it's not in any data centralized databases, or it's not collected in any orderly fashion either. And this study was carried out by Maersk Line when it tracked and analyzed one of these kind of shipment it handled. Then another example of maritime data exchange is what kind of touch points there are during a port call of a vessel. So this map here shows you what happens when a vessel comes into a port. So the blue line in the middle is the vessel. And when it's approaching port, different things start to happen within the port and with the different factors in the port area. For example, the pilot is informed that the vessel is arriving at a certain time. This means that the pilot has to start the preparations. Then also dock companies are informed if escort docks are needed to assist the vessel in. And usually when the bigger the vessel, more docks are needed. So usually you may need an escort dock to assist the vessel into the port, and then you need harbor docks to push the vessel into the quayside. Then Vessel Traffic Center VTS is also informed about the vessel's arrival. Ship agent is informed when the vessel is coming in, and also the ship agent is informed if the vessel has certain needs, for example, if they need fuel, if they need food deliveries or fresh water, electricity, and so on. And then also port is informed about the vessel arrival. And then port starts their own preparation. For example, the linesmen are ready when the vessel is near quayside. And then the terminal is of course informed as well. So they are ready to discharge the vessel and take the cargo out and put in new cargo in when needed. And then everything happens then in the vice versa order after the loading of the vessel is completed. So then all the actors are involved again, and everything is then done in stepwise approach in a reverse order as well. The challenge here is that initially everything is usually in national systems or ports' own systems, and everything is centralized. But the challenge is if something is updated. For example, if the arrival time changes, then this is usually telephoned by the vessel. So they call the port and then inform, or they call their agent and inform that we'll be arriving 2 days later. Then they inform the same information to the port authorities and other stakeholders, and then they are updating their systems based on this data. And usually these updates are then carried out by emails and telephone conversations, and some cases only on paper. So then when something is updated, the actual data is lost after that quite often. At the moment, there are loads of different kind of projects and research projects which are funded by different governments and EU funding and other possible funding mechanisms to address this issue of data sharing and data storage especially. And as mentioned, one of these is this just-in-time port call concept. And this is something I will introduce in upcoming slide. And the complexity of this whole system is one of the things which is resulting into really this kind of protectionism of data. And the reason for that is that because it's complex, people don't want to open it up for anyone else. And they want to keep how things work to themselves. And this leads to data being stored in various own locations, C drives, and so on. So it's kind of one of the big bottlenecks of going forward and how to start optimizing the things and sharing information. Hopefully, gradually we will see change in this attitude as well. Then a few words about the just-in-time concept. So basically the idea here is that today, for example, when vessels leave departure port, then they are informing the arrival port of their arrival time. But there may be changes when the arrival port can take the vessel in. So for example, if it looks like the vessel who is currently in that quayside position, it will take longer for them to unload the vessel, or they have had an engine failure and they need to fix it there, or for some other reasons, there is a delay that the vessel can come in, for example, 4 days later, instead of coming in at, for example, in this graph, you can see that the vessel is scheduled originally to coming in on day 14, but instead the port can take the vessel in on day 17. So what they usually do today is that they just go full speed, and when they arrive on day 14 to the port, then they will stay in the anchorage and wait there until the port can take them in. But instead of doing that, if they would implement and use this just in time, so then they would, when they get the information of the delay, which is usually coming in pretty early in the voyage. So it's not, sometimes it's of course last minute changes, but then it's some hours only, the delays. And the day level delays are informed quite well in advance. So when you get the information, then you can start slow steaming. So slow steaming means that you can reduce your voyage speed to an optimal level, and then according to the arrival time that when you're needed. So instead of steaming full ahead with full fuel burn, you can reduce the speed and reduce also the emissions you're causing. So this will have an effect on multiple factors also, this just-in-time operation. So in addition to the reduced emissions, the arrival time information has an effect on ports, who will inform when they can take the vessel in and when all the actors needed are ready. For example, when the stevedores can start unloading the vessel and loading the vessel. Also, the vessel informs port when they will actually arrive. So this is updated on a daily basis, and then it can also be predicted. So quite a lot of ports are at the moment using geofencing locations, so looking at vessels' voyage data and also certain geofences and estimating from there how long it will take for the vessel to arrive. Then if we look at the savings gained from the just-in-time concept, we have terminal operators who are getting savings through optimized resource use. Same for the port authorities. Ship owners can generate savings through reduced turnaround times. So when they don't have to wait, all the waiting time is cost for ship owners, of course. Cargo owners get reductions through reduced lead times. So their cargo is moving all the time and not waiting anywhere. And then, as mentioned earlier already, the reduced emissions. So just by reducing the ship speed by 10%, that will cause 27% reduction in the emissions, which is quite significant reduction. Then a few words about the autonomous maritime and how it looks like. If the world would be perfect and everything would be ready for autonomous ships today, then we would see that vessels are driven by data instead of being driven by persons with, for example, time schedule pressures. This means that control of vessel changes from direct equipment control to mission-based control. So today, vessels are controlled in a manner where you have a captain who is controlling the speed and direction of the vessel. But in an autonomous world, how we see it is that we change the concept of operating vessels quite drastically. So you go into a mission control. And the mission of the vessel usually is to move cargo from one place to another. And the main driver there is usually the arrival time. Or it can be something else. For example, if it's a tanker, the driver of the vessel can be oil price, for example, which will then determine how fast and at what time the vessel should be in port, or different port, or picking up oil, or something else. So for a fully autonomous vessel, the means of controlling vessel and the purpose of how vessel is controlled will change, and that will be more of a data-driven decision-making process instead of today's human process. Then also vessels will generate vast amount of data, which can be utilized by others. One example is vessel route and waypoint sharing for collision avoidance and route selection purposes. So at the moment in vessels, the crew of the vessels are monitoring what's happening around it, and the actions are based on what they are predicting the others will do. But in autonomous world, we expect that this situation will be changed around in a manner that the vessel, our own vessel, will inform the others what are our intentions. And with sharing this information, the others can prepare and act upon that data instead of operate and trying to predict what the others might do. Then also data drives fact-based decision making. So when you have more data available from the full voyage, then the decision making process is changed quite drastically, and also you can make different kind of decision based on the information available. For example, you can start linking up the behavior of oil market and weather and different factors into your voyage schedules. For example, if you in tanker cases, because in tankers a lot of money is tied up into the cargo itself, and the value is changing based on the oil price. And also then, of course, we have autonomy based on data models. So the more data we have, the better prediction models we can build, and also the better data models in that sense that you can have different kind of scenario models for different kind of things, which are not possible today to some extent. But then, of course, we have to always remember the challenge of maritime is that there is never two similar days. So the factors, external factors are always changing, and it's creating models is difficult, and that needs to be taken into account as well. Then when looking at the fully autonomous vessel, what kind of systems does it need to have, and where we are today with these systems? So this illustration is from Maersk Line, and this is how they have predicted the future and what kind of systems need to be in place in order for autonomous vessels to succeed. So first of all, what do we have in place in maritime at the moment? We have situational awareness systems looking what's happening around the vessel and outside. And I will have a few slides on that one, because that's something that our company, Growth Technologies, is focusing on, is the situational awareness side. To some extent, we have vessel connectivity in place already. We do send data out of the vessel to office side, for example, and vice versa. Then we have control and optimization algorithms also in place that optimize the movement of the vessel in most environmental friendly way, or schedule dependent way, or optimal fuel burn, or whatever the critical factors are that the vessel or their owner wants to optimize the voyage based on. Then we have a couple of solutions which are almost there, are being developed, but not necessarily not in full use at the moment. Electrical propulsion systems we have, but we don't have at the moment fully electrical systems that would be usable on ocean liners. So for example, a battery-based system, there is not enough battery capacity to operate, for example, a large container ship at the moment, fully electric. Condition-based monitoring and predictive maintenance, we do have solutions for those in place, and predictive maintenance is something that has been used quite a lot in recent times, in new applications at least. But still, a lot of these solutions are based on that the fixes are mostly made on board by the onboard crew. And that for autonomous ship, if it's unmanned, then it's of course not possible. Currently, there are some demonstrations for IT infrastructure in place for autonomous vessels, how it could be laid out, but not comprehensive approach for that. So not for any, for example, an ocean-going vessel which is going between continents. For that kind of vessels, there is no IT infrastructure in place at the moment. And there are land-based control centers. A lot of the larger companies have monitoring centers where they monitor their fleet. But for if they need to intervene and control the vessels, that kind of solutions are not in place at the moment, where you could globally control vessels. Then the systems which are more or less missing at the moment are the reliable prime movers and auxiliaries. So if you would operate a vessel without human intervention from, for example, from US to Asia, then for that there is no system in place yet mechanically that could move the vessel the whole voyage without intervention, taking into consideration also the possible failure cases. There is no real-time stable and secure high bandwidth connectivity. You can use satellite connectivity, but that is not stable and secure all the time. It is secure, but not stable. So that is something that is missing, but over time, we believe that this connectivity issue will be solved by the normal demand of humans for connectivity. If we take, for example, a cruise liner at the moment, there is a high demand from the people traveling on cruise ships that they want to have 24/7 connectivity, and they want to be able to stream Netflix videos in their cabins and so on. So this also means that this connectivity requirement is feeding for the commercial maritime in other use cases as well. Because when the companies are starting to improve these low orbit satellite connectivities and making them cheaper, then they are also usable for the commercial shipping in other means than just the entertainment means. Then autonomous control system, these are being developed at the moment, but not necessarily yet ready for full implementation. There have been technology trials, they have been used in different types of vessels, but not in 24/7 commercial operation yet. So there's still some way to go. And one of the critical things at the moment is, for example, the collision avoidance and how that will be arranged in future. Then here's one slide looking at why we are not there yet, why autonomous vessels are not reality at the moment. So one of the main things is the legal side of things. And then, of course, the definition issues is one big thing as well. So for the terminology, the autonomy levels have been defined, but still one term can be interpreted in many different ways. And then this goes back to the legal side of things, where you should be able to define how one thing is done and have it 100% clear and no other interpretations are available. Then we have the cybersecurity risks and the connectivity issues. So that's something that is, I think, for all autonomous systems is a similar issue, but the big thing is no guarantee of global connectivity, and hopefully this will be resolved in the coming years through the introduction of new types of low orbit satellite connectivity solutions and such. Crew issues, or the absence of crew issues. So currently the law defines that all ships must be in charge of a master, and the officers who will be who have appropriate qualifications. So the maritime law does not recognize a vessel without a crew at the moment. So there is these kind of legal issues and definition issues that need to be addressed. Same applies for issue of seaworthiness and error in navigation. So from insurance point of view, vessels have to be seaworthy, and there are different kind of definitions how it's defined to be seaworthy. And one of these things is that the ship must have proper manning, and also for watchkeeping. So they have to have watchkeeping held at all times, and this has to be done through the windows. That's how it's defined in the legal perspective. So things like these need to change in order for autonomous vessel to be commercially viable. Navigation rules, same thing here. It is expected that all ships will be capable of executing maneuvers and steering in accordance with the basic rules of navigation as prescribed in the collision regulations. And then the liability and the limitations regarding liability. So civil liability in shipping is regulated nationally, and it can be said that most jurisdictions require a fault-based standard. So there needs to be liability regulation changes also for autonomous vessel and how vessels are treated. Because at the moment, if you have an autonomous vessel, it doesn't have any crew members, then by liability regulations at the moment, whoever finds that can keep the cargo. So that's how or why, for example, in case of accidents like the Suez Canal, the insurance payments are huge. So in case of the Suez Canal issue some months back, the salvage company are entitled to liability or are entitled to get liability payment out of the company who owns the cargo or the ship and has insured the cargo. So they can state that how much they want from the salvage operation. And it's usually quite big numbers, and it can be quite devastating for the shipping companies to pay out all the required costs. Then for the autonomy level definitions, on the left-hand side, you can see the IMO, so International Maritime Organization's definitions. Level 1 is ship with automated processes and decision support. Level 2 is remote controlled vessels, but still seafarers on board. Level 3 is remotely controlled ships without seafarers on board. And level 4 is a fully autonomous ship. So level 4 vessel can make the decisions on its own without any intervention from humans. Then when looking at the introduction landscape, there are different kind of push factors, pull factors, and also weight of history that are affecting the introduction. For example, if we look at the pull of future, of course, technology is always something that is creating a pull, and future technologies are always exciting. So there is certain pull of future from technology side, and of course from environment side, because autonomous vessels are by default or should at least be more environmentally friendly. Same from society, there is some pull of future from that side as well, from education point of view, for example. And one thing also is that there's a lot of seafarers who would like to work rather from 9 to 5 instead of being 3 months on board a vessel in the middle of nowhere without any connectivity, for example. But then when we look at the bottom line of this chart and look at the weight of history, then we have, for example, from politics side, we have the slow regulations, which is hindering the process and making it really slow to introduce changes globally. From economy point of view, the ship owners, of course, there is risks for the first movers, and also to some extent the companies are more or less satisfied with the existing situation, and there is no push in that sense to make the change unless someone makes it. So if one company is making it in a large scale, then the others of course are interested and will be following up. Then of course one technology way of history is the life cycle of vessels, and as mentioned in the beginning and in the first slides, the age of vessels is really old. So vessels built today will be in operation still in 2050, which is something that we need to take into consideration. So whatever is introduced now, it will be more or less still in operation in 30 years' time. So that's one of the reasons also for the owners to be a bit of cautious about introducing different technologies if that technology hasn't been matured enough yet. So they want to be sure that the technology is still there in 30 years' time, because they will be operating vessels for so long. Yeah, then of course you have the push factors. So governments are supporting the change, for example. The green awareness in society is pushing more environmental friendly solutions out. Climate change is a big issue and environmentally, and things like these are then pushing autonomy forward. But we need to strike, of course, a balance between all of these different factors and take all of these different things into consideration. A lot of things I've been talking about is related to the legal framework and the complexity of that. So here is just one picture slightly explaining this challenge. So the yellow area here in the image is something that is covered by national rules and regulations. So for example, US or Finland or Norway, or to some extent it can also be on an EU level, for example in Europe. But there are national rules and regulations that need to be taken into consideration, and that which are driving the lawmakers. But then the other thing is the international side. So when we go into international waters, that's when the international maritime regulations come into place, and UNCLOS, so United Nations Convention of the Law of the Sea regulations. So in order to have, for example, an autonomous vessel, it has to comply with the national rules and the international rules if it's going into international waters. And the main challenge here at the moment is on the international level. So national rules are quite flexible, and a lot of countries are already creating enabling rules for autonomous vessels. But then on the international side, whatever new rule is introduced internationally in IMO, it requires that all member states unanimously agree with the new rules. So if one country is against the new rule, then it's not being introduced. And this means that the introduction of rules takes a really long time. So it can take up to 15 years to introduce something new. And just as an example, the change work has been started for introducing autonomy-related new regulations. And it took 5 years for International Maritime Organization just to carry out the scoping exercise. So just to review the existing rules and look what should be changed. So nothing has been changed yet, but this process alone has now taken 5 years. And that's why to change the rules and regulations in maritime, it takes approximately 15 years. So you can imagine it's not a fast process to take, and it takes long time. And that's why the regulations always, when something new is introduced, it is thoroughly evaluated if it makes sense, because when it's been introduced 15 years or coming into force 15 years later, in some cases, if it's made too hastily, then it's technology might be old or something else. So it's some might say it's a painstaking process. But for autonomy, where are we now? A lot of research has been carried out. So there's a lot of research programs, but there's also a lot of regulatory hurdles, especially on the international regulations. There has been technology demonstrations, and in principle, technology is there. There are some gaps still, but if we just look at national if a vessel would be operating in a national area, then it doesn't need satellite connectivity. It can rely more on mobile network connectivity and such. So for that kind of solutions, technology is in place and can be done. And there are the initial building blocks for autonomy are being worked on. For example, the situational awareness systems, there are quite a lot of companies bringing those to market, and the first systems are already being commercialized. On the right-hand side, you can see just an example table looking at some of the research work carried out. So in this table, we have how autonomous vessel would behave in different kind of situations. For example, if the vessel needs to be taken over, so there's an emergency situation and the remote control captain needs to take over the vessel control from autonomy system, then it's transferred to manual remote control. And the reason for this can be that the vessel has encountered a situation that it cannot solve on its own and it needs human intervention. And this kind of human intervention is expected to happen in many autonomy related solutions. Here's just some examples what are globally happening in this respect. So there are a lot of global initiatives ongoing. Moonin program was run in Europe. It ended back in 2016. Then in Finland there was our program that looked at coastal vessels and ferries and demonstrated the first fully autonomous ferry. Then in Norway there are initiatives in Japan as well, in China, Korea. So globally there are a lot of initiatives ongoing. In US, majority of the autonomy related activities are naval, so military side things, but there are also some commercial marine applications in the US in research works at least. Then what has been demonstrated and what is in operation. So from technology demonstration point of view, the first remote controlled ship was demonstrated back in 2017 by Rolls-Royce. It was done on a tug called Svitzer Hermod in Copenhagen. First autonomous vessel was demonstrated in 2018 also by Rolls-Royce on a road ferry called Falco in Finnish archipelago. So in principle, remote control and autonomous solutions have been demonstrated already, but in operation, at the moment we have remote controlled vessels in Belgium by a company called Seafar. They are operating inland ships, but these are mainly remote support operation. So they are from time to time operating the vessels, but they are also manned vessels, so the crew themselves operate them mainly as well. And then also for the autonomy side, there are autonomous commercial operations. One is being operated by Spacex. So the rocket recovery vessels are autonomously running vessels. A few bit more details on these applications. So in the demonstration of the world's first remote controlled commercial vessel, a new building DUG was fitted with the remote control capability. So there was forward and aft looking camera systems, LiDAR solutions to do a 3D scanning of the environment. Then it was fitted with connectivity. So the vessel was run fully on mobile network. So it was mobile connectivity from the tugboat to the remote control center. And you can see the remote control center on the top right-hand corner. And there the captain can fully control the vessel movements, but not the winches, for example. So it was mainly for the navigation of the remote control for the navigation of the vessel. And one of the interesting things was that on this demonstration, this was my team who did this. So initially we thought it would take some time for the captain to get used for the remote control, but actually it was only a couple of trials and he was really comfortable operating the vessel remotely, and he liked it actually more, controlling the vessel remotely more than being on board the vessel itself. Then the autonomous ferry. This was also my team that demonstrated back in the days when I was at Rolls-Royce. On this one, we did something called plug and play autonomy. So all the computing power was in a container, and we just put the container into the vessel and connected needed sensors to the container, and then we had the needed connectivity solution as well here. And the vessel was run from roughly 45 kilometers away from the remote control center, or monitored from the remote control center when it was in autonomous mode. And then when it was remotely controlled, the captain from the remote control center could drive the vessel himself from here. He had the possibility to run it from a joystick or direct manual control. So he had a couple of different opportunities from a redundancy point of view on how he wanted to operate the vessel. And on this case also, the connectivity was fully on mobile network. So we used the 4G cellular network to operate the vessel. There was also a possibility for Wi-Fi and satellite technologies, but those were not used during the control. So the control was fully from mobile network, and that was sufficient also to transfer the live video feed to the remote center as well. So it goes to just to show that you don't necessarily need satellite communications for remote operations. Then CFAR, it's one of the companies operating daily remotely vessels. They're operating this kind of inland barges in Belgium. Currently, they have 2 operation centers in operation, one in Antwerp and one in Rotterdam, and they are currently setting up additional one in Charleroi. At the moment, they have 9 ships under the management, and these 9 ships are all partially remotely controlled. So some of the time they are controlling them remotely from the center, and sometimes they are running by the captains on board. Then Spacex example. So Spacex is operating autonomously vessel called Shortfall of Gravitas, and they have 3 similar barges or vessels, and the vessels can drive themselves from port to the rocket recovery position without the intervention of crew and without towboats. But usually these are towed out just for safety reasons, especially in the port area. So in open seas, they are in autonomous mode. And as you can see, there are no windows, and everything is carried out by computers for the navigation and moving of the vessels. And these are used as the rocket recovery platforms. And these are originally converted from old barges for this purpose. So autonomy and data, where are we now? So a lot of data is already started to be generated. For example, a lot of image data. Data ownership is still an issue. As mentioned in the beginning, everyone wants to share data, but not their own. It's the same thing. Same applies also for machine learning. So for example, for machine vision learning, it's sometimes can be really challenging on generating enough data to create machine vision models. But there are companies who are working on new solutions to utilize the data. And for example, it's been used for insurance purposes to monitor ship performance and make new kind of prediction models, provide more accurate and close to real-time information for offices. For many, many years, there has been the only communication between office and vessel has been telephone and emails, but now office people and are getting more real-time information on the vessels, so they can adapt their operations more to what's actually happening on their vessels as well. Then it's been used by companies to optimize the performance and also ship performance. And as shown, there are remote control solutions coming into operation as well. One of the challenges here is, of course, the standards. So for data interfaces, there are not that many standards in place in maritime. So all companies who are developing these solutions are doing those in silos and not necessarily sharing in what format they are wanting to share the data between each other. Then just briefly a few words about the situational awareness systems. So these are the autonomy building blocks used, or the first building block for autonomy. So situational awareness system monitors what's happening around the vessel and utilizing machine vision with object detection and classification. And through sensor fusion of multiple data sources, the system can provide onboard fused information on the prevailing conditions and make it easier for the crew to make fast decisions where needed. So what our system at Grok Technologies is doing, it's fusing information from different sources. So we are using day and night camera, inertial measurement unit, and then also GPS information, and fusing this information together with the existing solutions on board, like sea charts, AIS, AIS stands for automatic identification. So each large ship is required by law to send their position information in AIS, and then radar is possible additional information as well. And all of this information is fused together and shown in a user interface to the users. Difference what's on vessels today and what we are offering as an add-on is that vessels today have electronic chart displays and radars, and then of course the bridge windows. And we are bringing, in addition to this, the sensor fusion based on the previously mentioned systems. So in our system, then we provide object detection and classification, which will then highlight what's happening around the vessel. It's also evaluating which of the vessels that are around us, for example, are a potential threat and which we need to take into consideration when maneuvering. Who do we need to avoid? Which ones are stationed, and so on. So it's just a decision-making aid at the moment for the crew on board. So then when looking at the future outlook, how does the industry look and where are we going in maritime? One of the big questions is, does the industry want to change? As it is, shipping is still by far the cheapest form of transportation. And in principle, if there is no real need for change, then it won't change. So there is, from commercial point of view, there is no need for autonomy because shipping is still the cheapest way of moving cargo from Asia to Europe, for example, or from Asia to US. And unless there is some other cheaper way, then there is no real drive for changing the status quo. Another thing is the industry is in many ways dominated by these conglomerates like Maersk Line, who set the pace of change. So if they want to go for autonomous solutions, then the others have to follow. But shipping is in that sense slightly different than other industries, that it's really hard for a small startup, for example, to distribute or disturb the industry as such as a whole. But that's why we are seeing this kind of autonomous applications in inland waterways, because that's an area where one company can start the disruption quite fast with a couple of vessels. But for global shipping, that requires a lot more. Emissions, big talking point, but will actions be taken? So that's something that remains to be seen. Recently, the COVID has opened a lot of eyes, and also the case of Ever Given in the Suez Canal when it blocked it. And the cargo owners want to know now where their shipments are, because a lot of cargo was stuck in the Ever Given, and the owners didn't know if their containers were on board or not. Also, industry has realized that as an aftermath that it's really fragile, the system at the moment. So if one canal is blocked, that will disrupt the whole supply chain for weeks, even months. But still, cargo carriers are reluctant to transparency and data sharing. So that hurdle has to be overcome.
So, this has been a very fascinating talk to really update us all on the state of the art and yet the headwinds that go with it. Unfortunately, we need to wrap in about the next 30 seconds. If you could, and this is the question that came in, if you could predict what's that one business case that would really move things forward, is there one or two, maybe data monetization or some other business case that would really move this ahead?
Yeah, I think at the moment, one of the things is that the inland shipping is the critical point here, because it will be used to demonstrate in small scale global shipping. So in inland waterways, there will be demonstration, and there are business cases where utilizing data from point to point. So not just for the sea voyage, but including also the other transportation means of goods and optimizing the whole value chain. I think that will be the best business case and where things will start.
All right. Well, thank you again for this very comprehensive look and a peek at how the data is helping drive this way forward. So this concludes our session.